one of the fundamental structures that is necessary going forward in discrete mathematics is the idea of a set. So a set, in really basic terms, is a collection of objects, and it's a very general definition. A set can contain names, it can contain shapes, it can contain colors, it can contain numbers, and typically in mathematics we think of numbers. As a real basic example, let's think about A. First of all, we give the set a name, almost always a capital letter, and let's define A as the set of students in Math 227. So the objects here are people, or maybe we would describe that set in terms of the people's names. As another example, let's take a look at set D. D is, and now you start to see these squiggly brackets. These squiggly brackets can be read as set of. So it's the set of the numbers 7, 13, and 22. So we could also describe the size of a set. Now, I don't know how many students are exactly in Math 227 at the moment, but I do see that in D there are 3 elements. So you probably remember the absolute value sign. And the absolute value sign we probably think about as just ignoring a negative sign if it's there, but what it actually means, if I take the absolute value of -3, it's really asking how many units from 0 is -3. Well, it's 3 units from 0. And so we'll use the absolute value sign to denote the number of elements in that set. So the size of D is 3 elements. Or we could just write 3, and that's usually what we do. And as another example, and a reserved symbol in mathematics, it's this fancy looking Z that sort of has these 2 legs down the center. And this stands for the set of integers. Now, integers you might think of as just 0, 1, 2, 3, 4, 5, and that's some of the integers, but integers could be positive or negative. So oftentimes you'll see it written as 0, plus or minus 1, plus or minus 2, plus or minus 3, and then we just do these ellipses to indicate that the set goes on forever. There are infinitely many integers. We can't list them all out. So when we look at the set, we can kind of see that the next element would be plus or minus 4, plus or minus 5, and so on. Now we've used the word elements. Those objects in that set are called elements. Okay, so the elements in D are 7, 13, and 22. We also want to be able to talk about membership in a set. So just like a person can be a member of a fitness club or a member of an organization, an element could be a member of a set. And we use this symbol here, and there's a number of different ways you could read this. You could use the word in, an element is in the set, or you can say element of, or you could say member of, or even belongs to. And we'll run across all of these variations, but as far as getting a comfort level, you can think about membership as the key phrase here when we talk about elements in relations to sets. So for instance, if I reference set D, it is true that 7 is a member of set D. Now I could also write it another way. Instead of writing the letter D, I could say 7 is an element of the set containing the elements 7, 13, and 22. So if we were at a fitness club and the person at the front desk was checking us in, they would look up to see, are we members of that set? The set being the collection of members of that gym. We could also say something is not a member of, and for instance, we could say 5 is not a member of D. So how do we do that? Well, we can't say 5 is an element of D or is a member of. So just like when we say not equal to, we can say not a member of by putting a strike through it. And that means 5 is not a member of D. 5 is not a member of D. Sets we've just described as a collection of objects, there are two key features of a set. First of all, unlike a list that you might encounter in a programming language, there are no repetitions in that set. So repetitions are just unnecessary. And also, the order elements are listed in does not matter. So in a list, if you've ever defined a list in a programming language and you list the elements as 7, then 1, then 3, that's not the same list as the elements 1 and 7 and 3, or 1 and 3 and 7 for that matter. But a set is useful in that we're not going to list any repetitions, and it really doesn't matter what order you list the elements in. If it does, then the set is just not an appropriate data structure. So to demonstrate 1, if I had the list of elements 1, 1, and 1 in the set, I wouldn't want to list it like that because it repeats the same element 3 times. I would just say it's the set containing the element 1. So those two are actually equal based on the principle that we don't need repetitions in the set. And that's just a demonstration of principle 1. Principle 2 is that the order that you list things in doesn't matter. So the elements 1, 2, and 3, although it's natural to want to list them chronologically, that's the same thing as the set containing elements 2, 1, and 3, which is the same as the set containing elements 3, 1, and 2. And there's some other arrangements we could come up with, but that's just an example of them. So you can all agree, we can probably all agree that if member 1, member 2, and member 3 are all members of a gym, then the order in which you read off their names is not particularly important. Okay, so those are the two features of a set. We can also relate two sets to one another. So a set A, in generic terms, is said to be a subset, sub meaning within or a part of another set B, if the following condition holds. Every element that is a member of A is also a member of B. And if A is indeed a subset of B, we use this symbol here that looks like an elongated C with a line under it. Now you may also see this, a situation where there is no underline. We're not going to worry about the distinction for now. So don't worry about the distinction here. This is kind of like the less than sign, that if you compare two sets, it kind of resembles a less than sign. If 4 is less than 5, for example, then it is also true that 4 is less than or equal to 5. And that's what this underline means here, is it's possible that those two sets could be the same as one another. So think about it as a less than or equal to, and it's just easier to stick with that. So if I gave you two sets and I said A is the set consisting of 1, 2, and B is the set consisting of elements 1, 2, and 3, and I look inside of A and I ask myself, okay, I see a 1 there. Is 1 also a member of B? Well, it is, right? They both have that element in common. 2 is an element of A, and hey, look at that, it's also a member of B. And since I've checked every element in A, and every element in A is also a member of B, it is valid to say that A is a subset of B. So in a way, it's kind of like less than or equal to. It contains at least all the elements. It contains all the elements. B contains all the elements that A does. So B is like greater than or equal to A, right? It possibly contains more. Like, for example, it contains a 3 here, which is more than A. So A is less than or equal to it. And that's how you have to compare them. We use the word subset instead of less than or equal to. But I want you to see that connection there. Now, if I went the other way around, if I said, is B a subset of A? Well, if I look at all the elements in B, well, 1 is in B. It's also a member of A. 2 is in B. It's also a member of A. But 3 is a member of B. It's missing, right? It's not inside of A. And so I would write that B is not a subset of A. That's not as common to see as the not an element of, or not equal to, but you could say that B is not a subset of A, since 3 is an element of B, and if it's an element of B, for it to be a subset of A, it would also have to be an A, but 3 is not a member of A. Now, an interesting fact can happen, and the question we might have is, well, what if they're both subsets of one another? Well, if I think back to the A and B example, A was a subset of B, but B wasn't a subset of A because B contained more elements that were not a part of A. So that might lead us to think, if all elements in A are also in B, and all elements in B are also in A, then they must be the same set. So I'll use that as an example where if A is in fact 1, 2, 3, B is also 1, 2, 3, then it's true that every element in A is also in B, and every element in B is also a member of A, and the conclusion that I could draw is that A and B are the same set. So that's a very useful concept because it allows us to assess equality of two sets.